So in this recording, we're going to talk about the dot and the cross product. So let's recall that in our introduction to vectors before, we talked about how we could add and subtract vectors to get a new vector, and also how we could scalar multiply a vector, so just multiply by some number to get a new vector. What we didn't talk about was multiplying vectors. And there's a good reason for this, is there's not a nice way to multiply vectors that acts like multiplication exactly how you would expect it to. So fortunately, there are a couple ways that are similar to multiplication that share a lot of the properties we want of multiplication, but not all of them in either case. So we're going to go ahead and introduce these. So these are the dot and the cross product. And we're going to go through the definitions here and an example and some properties. We'll wait until the actual classroom lecture to talk about why we actually care about these operations. So what good are they for us? So let's start with the dot product. This one's a little bit easier to work with. So let's suppose we have two vectors v and w. And so my components are x1, y1, and z1. So that means v is x1 in the I direction, y1 in the j direction, and z1 in the k direction. And similarly for w with x2, y2, and z2. So I'm going to define the dot product of these two vectors by just multiplying the components of I plus the components of y or j plus the components of k. So I take x1 times x2, I add that to y1 times y2, and add that to z1 times z2. Now notice that x1, x2, y1, y2, and z2, those are all just numbers. So this dot product is not giving us a new vector, it's giving us a number out of this. So when we're thinking about, well, why is this not a good way to define multiplication of vectors? Well, if you're going to multiply two vectors, you'd like to get a new vector out of it, not a number out of it. So that's kind of where this falls short of what you would really want for a true multiplication of two vectors. But it does share a lot of the nice properties that we would want out of a multiplication. So it is very important, like I said, to keep in mind that the dot product is a scalar and not a vector. So here's an example just so we know how to compute one. So let's let v be 2i minus 3j and w be minus I plus 5j plus 7k. So when we take the dot product, we're going to multiply the I components, which is 2 and negative 1. We're going to add that to the product of the j components, which is minus 3 times 5, and add that to the product of the k components. Now it looks a little tricky here because there doesn't seem to be a k component with v. That just means that's 0 times k. So the k component of v is just 0. So you get 0 times 7 for that part. So when we multiply these out, we get a minus 2 minus 15, so this dot product is minus 17. So these dot products are super easy to compute, which is one of the things we like about them. So now we're going to give some of the important properties of the dot product. You'll need to remember these properties. They're not hard to work out on your own, but you'll hopefully use them enough that you'll remember them, but they are important to remember. Now, why they are true isn't something that is going to be tested, but you should be able to follow along on why all these things are true because they're really just working out what the dot product is. So none of them are particularly complicated. So for the first thing we have is it doesn't matter which order the dot product is in. So v dot w is the same as w dot v. And this makes sense. If you were to multiply two numbers, it doesn't matter which order you multiply them. So this is something we might expect to have for multiplication. And so to see this, we just go ahead and compute each side. So if my vectors are as they were before, when I compute v dot w, I get x1, x2 plus y1, y2 plus z1, z2. And now we use each of these things are just numbers being multiplied. So if I multiply number x1 times the number x2, that's the exact same thing as the number x2 times the number x1. So we just switch the order of each of these. And then just notice that this second number here is exactly v dot w. So that's why this property is true. So you can see nothing complicated here. It's just going ahead and computing each side and seeing that we get the same thing. For the second property, we have a distributive law here. So if I take the dot product of u with v plus w, I can distribute that u. So it's the same thing as u dot v plus u dot w. So you can compare this to the regular distributive law for multiplication and addition with numbers. So this one looks a little messier, but it's really just the same thing. So now we have 3 vectors here. So we have subscripts of 1, 2, and 3 for our different vectors. So the first thing we're going to do is we're going to compute v plus w. So that's what's inside the parentheses here. And then when we dot u with that, we take the I component of u and multiply it with the I component of v plus w. So x1 times the I component here, x1 plus x2. And similarly with the y components and z components. And now if we go ahead and distribute these things out and then reorder the terms, so all of the, so we just distribute these things out first, and then we can reorder the terms. So take the x1, x2, y1, y2, and z1, z2, and write those ones first, and then the x1, x3, y1, y3, and z1, z3 second. We see this first term is u dot v, and the second term is u dot w. Now if I have a scalar, so remember a scalar is just some number, if I take that scalar and multiply it by whatever number I get from v dot w, that's the same thing as if I first did the scalar multiplication on the vector v and then dotted with w, or if I first did the scalar multiplication with w and then dotted with v. So again, these are just calculations here. So if I look at c times v dot w, first I do the v dot w in the parentheses. Now I can distribute that c across because now these are all just numbers being multiplied. And so I can put the c with the x1, the y1, and the z1 when I distribute. And then just notice that's exactly c times v dotted with w. And then same thing for the second term. In that case, I just distribute the c to the second term in each of the products to get the c times w. These are all just following from properties of real numbers and how multiplication and addition of real numbers is working. Now this property is particularly important and is one of the reasons we're going to be interested in the dot product. And that's if I take a vector and I dot it with itself, I get the square of the magnitude of that vector. So in this case, we can see the dot product is somewhat measuring the size of the vector. So again, just do the calculation. So v dot v is x1 times x1 plus y1 times y1 plus z1 times z1. And that's just because v is equal to itself, so we get the same component each time. So this gives me x1 squared plus y1 squared plus z1 squared. And I can rewrite that as the square root of x1 squared plus y1 squared plus z1 squared squared, which is exactly the magnitude of v squared. So that's it for the dot product for now. Like I said, we'll see why we care about the dot product more in the actual classroom discussion. But now let's move on to the cross product and see how this works in some of its properties. Now this one's a little bit more complicated to do, more complicated to calculate, but it is very important and is very useful for what's going to be coming in this course. So in this case, we actually do input 2 vectors and we output another vector. And this is called the cross product. And so you might think this is exactly what we want for multiplication, so why are we not just calling this multiplication? But we'll see one very important property that this does not satisfy that you would want multiplication to satisfy. So we need a little notation. So if you happen to have seen determinants before, this will be familiar to you, but if you haven't, that's okay. We're only going to need very basic determinants here. So the first one is if I write numbers A, B, C, and D in an array like this, which is a 2 by 2 matrix, and I take what's called the determinant, which we're going to use just vertical lines to indicate. You take the upper left entry, multiply it by the bottom right entry, and then subtract the upper right entry times the bottom left entry. So this times this minus this times this. And now we'll also need one when we have a 3 by 3 matrix. So there's lots of ways to compute this, but for us, the way we're going to care about is I'm going to start with this term here, the A. Now I'm going to think about using my fingers to cover up the first column in the first row, and then I'm going to look at what's left over here, this bottom right, and I'm going to put the 2 by 2 determinant of that in front of the A. And now I'm going to move over to B, and I'm going to use a negative sign now, so they just alternate in sign. You just have to remember that. And so I'm going to think of covering the first row up, and now the column with B And what I'm left with is D, F, G, and I. So that's going to go in this determinant. And then finally I move to C. I switch from negative to positive, cover up the first row and the first column, and what I have left is D, E, G, and H. And now you can evaluate these ones, these three determinants here, by the formula above. So we're going to have lots of practice with this, so you'll get used to this formula. But we're going to write out the exact formula once we actually do this evaluation on the next slide. But this is how you should remember to do it. So you're not trying to memorize some giant formula, because then you get on the exam and you forget what the giant formula is and you make a mistake. So just remember the process here. You need to remember this formula and then this process here. So how we're going to describe or define the cross product of our vectors is we take V and we write an X here, so V cross W. And now in the very first row, we're going to put I, J, and K. The second row, we're going to put the components of V. And the third row, we're going to put the components of W. And now we're going to calculate this just like we did on the last slide. So you take the I, you cover up the first column in the first row, and I get Y1, Z1, Y2, Z2, so this part's left over, times I, switch the sign, so negative. Now I'm going to cover up this column in this row, and I get X1, Z1, X2, Z2 left. And finally, switch the sign back to positive. For K, I cover up the first row in the last column. I get X1, Y1, X2, Y2 here. And now if we go ahead and evaluate this, remember it's this Y1 times Z2 minus Z1 times Y2, and I'm just going to write them in alphanumeric order here. So Y1 Z2 minus Y2 Z1, and same thing for the other terms here. So this is the actual formula that you can plug the numbers in. Like I said, it's easy to mess up this formula if you just try to remember it. So it's really best to remember the process of how you get to this formula and do that process each time. So let's do a really simple example here. Let's just take the unit vector I and cross it with the unit vector j. And so in terms of components, I is just 1, 0, 0. And in terms of components, j is just 0, 1, 0. And so if we do this out, notice the first term is going to be 0 times 0 minus 1 times 0. So that's going to be 0. 1 times 0 minus 0 times 0. So that's going to be 0. And then I get a 1 times 1 minus 0 times 0. So we see that the unit vectors I cross the unit vector j just give me the unit vector k. Okay, so let's see some properties now of the cross product that are important. We're going to show a couple of these, but not all of them, because they get very messy to actually write out the details of. So the first one, and this is kind of why we don't want to think of the cross product as exactly like what we would want multiplication to be, is because the order actually makes a difference here. So if I take V cross W, it's not the same thing as W cross V in general. It's the negative of W cross V. So if you switch the order, you have to introduce a negative sign. And we know for multiplication of numbers, we'd expect it not to matter what the order is. So here, if we just write out the definition from the previous slide, just notice if I factor a negative out of this, it changes the order. So if I pull a negative out, I get y2z1 minus y1z2, and similarly all the way through. And then this new term inside is just w cross v. So that's where that negative comes from. You're just switching the order of everything. So again, you can work this out by hand. It's not hard to do. You're just writing down the definitions. But the important thing is you do need to remember this property, even if you don't remember exactly how to show it. If I take any vector and I cross it with itself, I get the zero vector. Now remember, a vector cross a vector is always a vector. So this 0 is not a number, it's a vector. We have to keep that in mind. That's why we're using a bold here for this to indicate it's the 0 vector. So this would be 0i plus 0j plus 0k. And so if we just write this out, we just see since the components are the same, I get y1z1 minus y1z1 and so on. So each of the components here is 0. So we just get the 0 vector back. For property 3, I have if I take the cross product of v cross w and I dot it with v, I get 0. Notice that this is a number because I'm taking a dot product of two vectors, and that gives me a scalar. And same thing if I do w dot v cross w, I get 0. Again, number, not a vector. So let's just do the computation for one of them. So if I do the cross product, I get these terms in the parentheses. And then to dot that, I take the first component of v, multiply by the first component of v cross w, and so on all the way across. Now if we just FOIL everything out, we see that we get cancellation. So here I have an x1, y1, z2, and here I have a negative x1, y1, z2. So those two terms cancel. And you can see all the way through. And now this property seems like kind of out of nowhere, and it doesn't seem as natural as the other ones we've looked at. This is going to be super important, and we'll see why when we get to this when we get to the class lecture on this. And here's just some other properties we're not going to show because they're just tedious. You can write them down if you like to. It's just a matter of writing down all of these definitions and working through. So again, we have a distribution law, so I can distribute the cross product over addition. I can move a scalar in, so scalar times v cross w is the same as c times v cross w or v cross cw. And then finally, if I take the cross product of any vector with the zero vector in either order, I get the zero vector back. Okay, so like I said, you can write all of these down just using the definitions. It might be good practice to go ahead and pick one of them and write out the details to make sure you understand how that works. But for now, we're just going to make sure we know the properties and know how to use them because they'll be important in what comes next.